Now here we derive a very important relationship between continuity and differentiability. So here goes the theorem, which in simplest words says that every differentiable function is also a continuous function. Right. So what it says is, if we have some function, say y, as a function of x, which is a differentiable function of x, then it is also the continuous function. So that means we have a kind of implication here, logical implication, that is differentiability implies continuity. Okay. And now let us prove this. That is, let us consider the function y as a function of x, which is a differentiable function. And by the word differentiable, it means it can be differentiated. That means its derivative exists. And we are aware the derivative is denoted by f dash of x, and it is defined as the limit of f of x plus h minus f of x whole upon h as h tends to 0. So here let us consider some arbitrary point, that is, say consider x equal to say c. Okay, at some point we are discussing the meaning of this particular relationship. So therefore we can say that the function, since it's differentiable, we can calculate or write an expression for its value at x equal to c. So we have f dash of c is equal to limit of c plus h minus f of c whole upon h as h tends to 0. Right? So since the derivative exists, we write the expression for that derivative. Okay. Now let us consider the expression which is in the numerator of this particular definition. That is, let us consider f of c plus h minus f of c. Now I will just divide and multiply this particular expression by h, because we know h is a non-zero quantity. It is reducing and becoming 0, but it has not become 0 yet. Okay, so therefore we can definitely divide and multiply by h. Now let us take the limit of both sides as h tends to 0. Alright, so therefore we can say that limit of f of c plus h minus f of c, this is the left hand side, as h tends to 0 equals the limit of the right hand side. And in the right hand side we have a product of two functions, so therefore we will take the product of their respective limits also. So therefore we can write limit of f of c plus h minus f of c whole upon h as h tends to 0 multiplied by the limit of h as the same h tends to 0. Now clearly the first bracket is nothing but f dash of c, which we have already defined and kept ready, whereas the second bracket is definitely tending to 0 because h itself is becoming 0. So therefore as a whole the right hand side will become 0 when we replace the limits. So therefore this entire right side is equal to 0. Now if you look at the left hand side, when we take the limit of f of c plus h as h tends to 0, that means we are basically taking the limit of the function f of x as x is coming closer to the value c, because in other words the difference between x and c, which is nothing but h, that is tending to 0. Right. So therefore we can write limit of f of x as x tends to c. That is what is the meaning of the limit of the first quantity, that is f of c plus h as h tends to 0. That is same as limit of the function as x comes closer to c. Now the second quantity is minus limit of f of c as h tends to 0. Now if you see, c is an arbitrary constant because we are considering some arbitrary value of x. So clearly f of c is a constant, and hence as h tends to 0, f of c will have no effect on that. So therefore limit of f of c as h tends to 0 is same as f of c itself. So therefore we keep f of c as it is, that is equal to 0, and here the limit is only of f of x, right? So therefore finally we get limit of the function f of x as x comes closer to c must be equal to value of the function at x equal to c, and this is precisely the definition of continuity. So we have proven that if the function is differentiable, then it is necessarily continuous also. But we have to keep in mind that the converse of this theorem is not always true. That means if a function is continuous, then it's not necessarily differentiable. It may be differentiable or it may not be differentiable, but it does not imply that it has to be differentiable if it is continuous. So as an example of when the converse may not be true, the simplest example is that of the modulus function, right? So let us see the modulus function and understand how it does not make the converse true. So if we see the modulus function, the graph of modulus function is familiar. That looks like this. Now here at x equal to 0, if you observe, no doubt it is continuous because the limit of the function from both sides tends to 0. But if you see the derivatives taken from both sides, that is left hand derivative and right hand derivative, clearly the left hand derivative is -1 because the slope of this particular left side portion is -1 and the right side portion is +1. So therefore at x equal to 0, the two derivatives, the two sided derivatives do not have the same value. So therefore at x equal to 0, the modulus function is not differentiable, although it is continuous at x equal to 0.